In the last lecture, we were discussing the flow in a rectangular channel. If you recall, we were discussing the flow in a rectangular channel of width w in the y direction, height h in the z direction, a unidirectional flow, steady, fully developed, governed by this equation, where dP dx, the pressure gradient in the x direction, is a constant for a fully developed steady flow. And the second term on the right there is the Laplacian of the velocity in the streamwise direction, x direction. Okay. The second derivative with respect to z and the second derivative with respect to y. With boundary conditions, Vx is equal to 0 at y is equal to 0 and y is equal to w, that is, the velocity is equal to 0 at the two vertical walls, and at z is equal to 0 and z equals h, the two horizontal walls. At both of these, the velocity is equal to 0. Since the velocity is equal to 0, it can be, the velocity can be expressed as the sum of functions which reduce to 0 at the walls, orthogonal functions which reduce to 0 at the walls, because any function can be represented as the sum of the orthogonal functions times coefficients, and those coefficients can be determined from the orthogonality relation. Okay. So, that is the principle that we had used. So, we had expressed Vx as the sum of sine functions in the y direction and sine functions in the z direction with the periodicity with the period of the or the wavelength of these functions chosen so that they are 0 at all four walls. We substitute that into the equations. The second derivative with respect to y and the second derivative with respect to z are both sine functions themselves. We substitute that into the equations and then use the orthogonality relations. Okay. To get what is the value of, okay, we get an equation of this kind, okay, which contains the pressure gradient and these coefficients a m n determined from orthogonality, okay, from these two orthogonality relations. Okay. The coefficients a m n determined from these two orthogonality relations. So, these were the expressions for the coefficients. We substituted that back into the expression for the velocity, and we got an expression for the velocity field as a function of y and z. The summation of coefficients, the summation of some coefficients which depend upon I and j times these sine functions. Okay. The flow rate was obtained by integrating the velocity over the y and z directions, and the average velocity is the volumetric flow rate divided by the cross sectional area, that is w times h. Okay. And on that basis, we had got this expression for the average velocity. Okay. So, now that we have the average velocity, we can find out what is the friction factor. Okay. F is equal to 1 by 2 rho V average square dP by dx. Okay. The negative sign, because dP by dx has to be negative if the velocity has to be positive. Okay, the negative sign. Okay. This is the solution for a laminar flow. Okay. We have assumed that the Navier-Stokes equations apply, and therefore, this is a solution for the laminar flow. We did not include any convection due to turbulent fluctuations in our description. So, this is for a laminar flow. I can write this as mu by rho V average times. Okay. Okay. So, in order to simplify the problem a little bit of finding out the friction factor, I will just assume, okay, square channel W is equal to H. Okay. Assume a square channel, W is equal to H. You can do it for a more general case as well, okay, where W is not equal to H. The procedure is exactly the same. For the present, I will just assume a square channel for simplicity. Okay. So, the hydraulic radius of the square channel is going to be equal to the perimeter, okay, the perimeter, okay. The perimeter is 4 times H, okay. I am sorry, it has to be the area by perimeter. Area is H square by 4H, okay, which is equal to H by 4, okay. And the equivalent diameter is equal to 4 times RH, which is the same as the side of this square channel, okay. The equivalent diameter is 4 times RH, that is the square, that is the side of the square channel. So, I can scale it by H itself, okay. F is equal to 1 by 2 rho VAV square into minus dP by dx. Since this is a laminar flow, I would expect the friction factor to scale as 1 over the Reynolds number. So, I will write this as mu by rho VAVH, okay, into 1 by mu okay, into H by mu times VAV times dP by dx. Okay, so, this scales as 1 over the Reynolds number. I should have a factor of 2 here. Okay, so okay, this factor of 2 is there. And the friction factor should actually have a factor of the diameter in it. So, let me write it again for you. The friction factor should have dimensions of dimensionless, that means that it should have 2 rho V average square divided by H for a square channel. Okay. And I can write this as mu by rho, okay, because H itself is the hydraulic diameter, okay, okay, into H square by 2 VAV mu into minus dP by dx. Okay. So, is equal to 1 over the Reynolds number based upon the average velocity and the height of the square channel into H square by 2 mu V average into minus dP by dx. Okay. And recall the expression for the average velocity here. Okay, recall the expression for the average velocity here, where I have left out this dP by dx. Okay, kindly correct that. Okay. I have left out this dP by dx. Okay, in my constants, kindly correct that, because this dP by dx has to appear here. Okay. This dP by dx has to appear in these expressions. Okay. So, this, as you can see, there is a factor of the viscosity there, okay, factor of viscosity, yeah, factor of viscosity here, okay, arising from this term here, factor of viscosity arising from this term here. Okay. So, I left out the dP by dx and the mu. So, the velocity is proportional to dP by dx divided by mu times this h square here. Okay. In this particular case, you will get a factor of h square over here. Okay. So, that will cancel out, okay, and ultimately you will get, okay, is equal to 1 over R e into this coefficient V average, okay, sigma into 1 by 2, okay. The dP dx will cancel out, the viscosity will cancel out, and h square will also cancel out, okay. And I will get summation I is equal to 1 to infinity, summation j is equal to 1 to infinity, okay, times 4 into 1 minus 1 power I whole square and this pressure term will cancel out, okay, the pressure term will cancel out, viscosity will cancel out, and this W square will cancel out, okay, because I am assuming that H is equal to W. Therefore, I will get whole square whole inverse, okay. Here I have assumed W is equal to H, so that W and H will cancel out, okay, over here, okay, because I have 1 over H square whole inverse. So, that gives you an H square in the numerator, okay, and that will cancel out with the H square that is over here, okay. So, in this expression, okay, and I take the derivative, this whole thing inverse because this V average is in the denominator, okay. So, this is the expression for the friction factor in a square channel. I can do the summation for a finite set of terms in this case, okay. If I take for example, okay, I is equal to 1 to 5 and j is equal to 1 to 5, I get a fairly converged result, okay. F is equal to 14.27 by RE. 14.27 by RE is the result for the friction factor in a square channel, sorry, 227. Okay. So, using this separation of variables procedure, we have managed to find out what is the friction factor correlation for a rectangular channel. I simplified it here for you for a square channel, but it is quite easy to do the same calculation for a rectangular channel for any ratio of length and height, okay, of width and height, okay. It's just a matter of substituting W and H into these equations and then simplifying the equations, okay. That's the only thing that needs to be done, okay. And using the appropriate equivalent diameter, which turned out to be equal to the side H for a square channel in this case. For a more complicated case, it may not be equal to the side, it will be will be equal to WH by 2 into W plus H, because 2 into W plus H is the perimeter of a rectangle and W times H is the cross sectional area of the rectangle. Use this relation and express all coefficients in terms of this relation and you will get the friction factor for a rectangular channel of any other shape. Okay. So, this is an example of how we had used separation of variables in order to find a solution, a series solution in both y and z for the velocity profile in a rectangular channel. From that we got the average, we got the total flow rate as a function of the pressure gradient. the average velocity as a function of the pressure gradient, and from that we calculated what is the friction factor, okay, using this expression. Okay. Friction factor goes as 1 over Re for a rectangular channel, and we calculated what is the friction factor in this particular case. Okay. So, that is for a Cartesian coordinate system. I have solved two problems for you. One problem where we have heat conduction, there was no source term, and so we had homogeneous boundary conditions in one direction and forcing in the other direction, and I showed you how to get the solutions using separation of variables. The second case, homogeneous boundary conditions in all directions, in the y direction and the z direction for the velocity, forcing through an inhomogeneous term in the equation itself, that is the pressure gradient, okay, and how to use that forcing in order to determine what is the velocity field, the flow rate, the average velocity, and from that the friction factor. Okay. So, with this we complete our discussion of separation of variables in a Cartesian coordinate system. Next, I will go to separation of variables in a spherical coordinate system. Okay. Recall that we had solved the heat conduction equation, okay, for the heat conduction from a sphere of radius r, okay, in 3 dimensions, spherically symmetric, with temperature T is equal to T0 at r is equal to r and T is equal to T infinity as r goes to infinity. The simplest case, a spherically symmetric problem where T is equal to T0 here and T equals T infinity far from the surface. And if you recall, the temperature field turned out to be T minus T infinity is equal to T0 minus T infinity into R by R. Okay. That was the solution for the temperature field, and recall that the equation for the temperature was 1 by r square T by dr of r square partial T by partial r is equal to 0. This is the spherical coordinate, okay, Laplacian del square T is equal to 0. In spherical coordinates, for a spherically symmetric system where the temperature varies only in r and it does not vary as you go around on a spherical surface, okay, it does not vary with angle on the spherical surface, it varies only in the r direction. So, this was the solution, okay. And we could also write this as Q by 4 pi k r, where k is the thermal conductivity and Q is the total amount of heat generated per unit time from the sphere. Okay. The heat flux times the surface area, that is the total amount of heat generated per unit time. So, this is the solution for the temperature field for a spherically symmetric system. We will go on to a slightly more complicated problem, okay, and that is the effective conductivity of a composite. Okay. You have a composite material which consists of a matrix, okay, in which there are inclusions, okay, spherical inclusions. Okay. It is of length L. Okay. And the temperature difference across is delta T. Okay. And the thermal conductivity of the matrix is different from the thermal conductivity of the particles. Okay. The thermal conductivity of the matrix is different from the thermal conductivity of the particles. And because of this, the effective conductivity, okay, if I write for the entire composite Qz, the average flux is equal to minus K effective delta T divided by L, okay. Macroscopic temperature difference divided by the macroscopic length scale, okay, minus into the effective conductivity. What we would like to know is how is this effective conductivity related to the conductivity of the particle and the conductivity of the matrix. Okay, so, that is the problem. And these are spherical inclusions which have a radius r and a conductivity Kp, okay, for particle. Okay, so, that is the problem. And we will consider this in the dilute limit, where the temperature field around one particle does not affect the temperature around another particle. Okay, so, that is the approximation we will make. So, if I had no particles, okay, and if I looked at the field, right, if I apply a temperature difference, okay, delta T across a length L, okay, the flux is just going to be equal to, okay, so if I take this as the z direction perpendicular along the direction of variation of temperature, assume that temperature varies only in one direction, then the flux is going to be equal to minus Km delta T by L. Okay, that is, the conductivity is going to be the same as the conductivity of the matrix. Okay. However, when you have some particles included in here, these could have either a higher conductivity or a lower conductivity than the matrix. Okay. So, in the absence of particles, the heat flux lines will just be straight lines, okay, that go from one surface to the other. Okay. The heat is being conducted only along the z direction, because that is the only direction in which there is a temperature variation. Okay. The temperature variation is only in the z direction, therefore, the heat flux is only in the z direction. Therefore, the flux lines are straight lines which have direction along Ez. Okay. Now, what happens if you have a particle in this matrix? Okay. If you have a spherical particle in this matrix, okay, this particle is going to distort the flux lines that are going vertically in the absence of particles. If the particle conductivity were greater than the matrix conductivity, okay, the flux lines would preferentially go through the particles. Okay. Okay, the flux lines would preferentially go through the particles. In the limit, as the particle conductivity becomes much larger than the matrix conductivity, you would expect the flux lines to be perpendicular to the surface. I told you that if you have a perfectly conducting surface, then there will be no variation in temperature parallel to the surface. That means that the flux lines have to be perpendicular to the surface. Okay. So, this is going to cause a disturbance to the flux lines within the particles, and therefore, the flux is going to be different from what it is when the particles were not present. Similarly, if I have a particle which has lower conductivity than the matrix, okay, less than Km, then the flux lines would basically go around the particles. Okay. The flux lines would go around the particles. In the limit, as the conductivity of the particles goes to 0, there will be no flux, because the particles are perfectly insulating, and therefore, the flux lines will not go through the particles, they will be tangential to the particle surface, as they pass around the particles. Okay. So, those are the two limiting cases, and because of this you are going to have the conductivity, the effective conductivity of the composite being different from the effective conductivity of the from the conductivity of the matrix. Okay. So, particle conductivity is greater, then the effective conductivity will be greater. If it is less, the effective conductivity will be less in comparison to the matrix. This we will consider in the dilute limit. Okay, where the volume fraction of the particles is small. Okay. Particles is small, okay, such that the disturbance of the flux lines due to one particle does not affect the temperature field around another particle. Okay. So, basically if you had two particles that are very close to each other, right, then the disturbance to the flux line around one particle is going to affect the temperature field around another particle, because the second particle is located in a zone where the temperature has been modified by the presence of the first particle. Okay. Okay, so, because of that, okay, you will have, okay, interactions between the fluxes in each particle, okay, interactions between the fluxes in each particle. Okay. So, here we do not consider that, we consider the dilute limit where the volume fraction is small, so that the flux lines around one particle, the disturbance to the temperature field around one particle does not affect the temperature field around another particle. Okay. So, it is the dilute limit, and in this dilute limit, okay, you can consider each particle to be placed in a temperature field. Okay. Okay. You can consider each particle to be placed in a temperature field, okay, which at infinity far from the particle is a linear temperature gradient. Okay. So, if you recall, in the absence of any particles, the temperature field will have a linear gradient far from the particle. Okay. If I plot the temperature, okay, as a function of this coordinate z, okay, if I take z is equal to zc is the center of the particle, the temperature will be very linearly about this location. Okay. Let me plot that again for you. Okay. Okay. Temperature difference delta T, the height L. Okay. In the absence of any particles, the temperature would have been equal to, okay, T the heat flux would have been equal to minus K T prime is equal to minus K delta T by L, okay, in the absence of any particles, where T prime is the gradient of the temperature in the z direction. Okay. So, that would have been the temperature field in the absence of any particles. Now, I have a spherical particle which is sufficiently far from other particles, and if I expand out the region around this spherical particle, this is in, okay, the temperature is varying in this the z direction, okay, and let us say that the particle location here is at z is equal to zc, okay, where z is the vertical coordinate here. Okay. Far from the particle, it is only matrix, and therefore, you have a temperature that is varying linearly with position. Okay. Okay. That is varying linearly with position of the form T is equal to Tc plus T prime z. Okay. T is equal to Tc plus T prime z is the variation in temperature far from the particle. Okay. Okay. Because we have a particle with a thermal conductivity that is different from the matrix, there is going to be disturbance to this temperature field due to the presence of the particle. What is the disturbance to the temperature field and what is the disturbance to the flux? That is what we have to calculate now. Okay. In the dilute limit, where the temperature around one particle is a linear temperature field varying linearly with z far from the particle, but which has a disturbance because of the difference in conductivity at the particle surface. So, I will continue this calculation in the next lecture. I will see you then.